All right, so if you ever need to figure out like where a lesson is, or if you want to get the notes or videos or see what you missed, whether you were late or maybe something unexpected happened when you were at home and you couldn't get to the lesson on time or whatever, for my P-Learning page, if you go to calendar right here, that second option, that second tab on the top, I'm going to have every lesson posted here. So it tells you what it is, what our target is that we're working on. This is just the first learning target today. And if you click on it, oh wait, let me show you the student view. So from here, you click on the day, and it just tells you like what we're trying to focus on. Print these out or anything. It's just there. If you missed an example, maybe I went too quickly in class, you can see what we're doing that day. And then the video, this is a link to a recorded video of my actual lesson that I taught. So it's just a YouTube link. I uploaded it. It's me talking. All right. So that's always there for you, just in case. All right. Now these recordings are always coming from my my first hour class, in case. So if it's like, wait, I don't remember Wojcik saying that in class. Well, that was because it's from the previous class, my first hour instead of my second hour class. But it's still the same lessons, and so it's always up there for you. All right, so just a nice little resource for you. Now today, I guess no more riddles. You don't want that. But we do have a lesson. So everybody, why don't you grab out a notebook and something to write with as I take attendance. Let's see. Okay. So this is our first learning target, 1.1. And we're just going to learn how to graph these absolute value functions. And easy enough graph to recognize because it looks like the letter V. In the blue box on the left there, I have this f of x equals, and then there are these two vertical bars surrounding the x. And those vertical bars, that's the absolute value symbol. It means we always take the positive value of a number that's inside there. And that f of x, that might look a little weird. I think you probably saw this in Algebra 1. That's just called function notation. And it simply means, it's the same thing as like y equals. You probably saw that a lot back in Algebra 1, like y equals mx plus b or stuff like that. So whenever you see f of x equals, you can just think of that as y equals. And here, the absolute value of x. So go ahead and sketch a graph. It doesn't need to be perfect or anything like that. Just do a quick x and y axes. Just go out to, I don't know, 2 or 3 on those axes. And there's some key points of this graph that I want you to note. First off, this one corner, that bend part right there, that's going to be called the vertex. V-E-R-T-E-X. Oops. And that's kind of like our main focus, our main point of the graph. That's the key starting point, the vertex. And that's the nook or the corner of the graph. And by default, this graph will always have a vertex at 0, 0, which is the origin. It's a great starting place. From there, it makes the letter V. Well, why does it do that? I've got on the left a t-chart here. So if we put in different x values, we see different y values, right? Like if I were to select a 1 for x, Then what would f of x be? Well, you just take the absolute value of x, and that gives you your f of x, your function of that x. Well, the absolute value of 1 is just 1, nice and simple. So we got to point at 1, 1. It doesn't even really change the number. It doesn't do anything to it. Same thing with 2. The absolute value of 2 is 2, so that's another point, 2. And this pattern will continue, 1, 1, 2, 2, 3, 3, 4, 4. It's going to go on forever, right? And so this graph, if you're starting at the vertex, you simply can figure it out by going right one, up one, right one, up one. And then to the left, what's going to happen? If you go left one, you still go up one. But why? Like if it's 1, 1, 2, 2, if I go -1, why isn't it also -1? Well, that's because if -1 is my x value, remember we're taking the absolute value of it, and the absolute value of a number ignores the signs. It's always just taken, I just care about the number. I don't care if it's positive, negative, whatever. I just want that quantity. So the absolute value of -1, it's a positive one. So from the origin, if I go left one, I'm still going to go up one. It always stays positive. Same thing for -2. Well, the absolute value of a -2 is a positive 2. Remember, I don't care about the sign. I'm just looking at that number. So -2, positive 2. And if you notice from the vertex, it keeps this same pattern going left 2, up 2, or left 1, up 1, left 1, up 1. That pattern just keeps on going forever and ever. Now, this basic version of the graph, this plain absolute value of x, is called the parent function. All right, that's like our starting graph. And today we're going to learn how to graph different versions of this v, of this absolute value, because the graph's not always going to start at the vertex, and it's not always going to be exactly that size. And so to figure out how these graphs are going to be changing, like if I put in some numbers and it's a function, if I'm adding numbers or subtracting it or things like that, it's going to move the graph around the coordinate plane. But our starting point is always going to be from this version right here, this plain old regular absolute value function. So it's called the parent function because it's like what you start with. Now the other ones change a little bit from this parent function. All right. Any questions yet? Did you look at these graphs in Algebra 1? The V-shape at all? Yes? No? You don't know? Okay. It's not too tricky. Now, you don't need to write all these down. This is just me showing you what we're going to learn today. So we're going to transform, which just means change. Like Transformers, right? It's a car, it's a robot. Oh my gosh, I don't even know. So we're going to change that function from these 6 different means. These are different transformations that can occur to our graph that's going to change it. It's going to move it around, it's going to flip it, going to change its size, stuff like that. So we're going to look at each one of these in more detail. Except this guy, horizontal flip, we don't really care about that one. Think about it, and we'll come back to it. Why do I not care about the horizontal flip? Starting off, the vertical translation. So jot this down. Write the function, just like I have here, f of x equals the absolute value of x plus 2. Make sure you write that plus 2 after the absolute value sign. So it's like you're taking the absolute value first, and then you're going to add the 2. And sketch that graph of the v also. Remember, the graphs don't need to be too precise. Just do a quick X, Y with little tick marks for the X and Y axis. And note where that vertex is. You know, it's obviously moved from the origin. Now, this one, if you think about our original parent function, that was just the absolute value of x. The only change here is this plus 2. Now, looking at that graph, you can kind of see what happens, right? From the original one, what happened to the v? How did it move? How did it change? Where'd it go? You can just shout it out if you want, you know, I know you all want to say the answer at the same time, I'm sure. So this one, vertex is at the 0. Here, where's the vertex now? Perfect. Thank you. Yes, it went up 2. So this plus 2 just made the graph move up 2 units. That's it. So this causes a vertical translation. Vertical means up and down. If I draw a little arrow. Translation just means it's sliding or shifting. All right, so it's not rotating around. It's just like it just jumped up 2 units. It stayed looking exactly the same, but this is a slide or a shift, I might call it. It just shifted up 2 units. Now, any ideas? If instead of a plus 2, if I wrote a minus 2, what do you think would happen to that graph? Where would that V move, do you think? Any ideas? Taylor, come on. Yes, down 2, right? It's just going to shift down 2 units. If you add something, it moves it up. If you subtract something, it moves down. And that's the vertical translation. It's pretty straightforward. So if I were to give you this equation right here, absolute value of x plus 5, you would draw that same V shape. You would just move it up 5 units, and that's it. You don't need to make another T-chart. You just start with that vertex and then kind of draw your the tilt of those angles, right? Over 1, up 1, over 1, up 1. Awesome. Next up, a horizontal translation. So the word horizontal just means left and right. So go ahead and write this equation down. And sketch that graph. You don't have to write the stuff in green. That's just kind of an out loud thinking question for you. All right, so here I've got the absolute value of x plus 4. Now that looks pretty similar to the previous one. I had absolute value of x plus 2, but what's the big difference here? Why did this addition move it sideways instead of up and down? What's the only difference? Anyone can talk. It's okay. I don't mind. Is everyone really sleeping still? A little bit. So where's the plus 4? Is it inside the absolute value or outside of it? Inside. Thank you. Yes. So notice with the vertical translation, the plus 2 is outside the absolute value. This one, the plus 4, is inside the absolute value. That's going to be the difference. That's what's going to cause the function to move left and right instead of up and down. And so absolute value of x plus 4 causes this horizontal shift. But what's a little weird about that? That says plus 4, but did it move to positive 4 on the x-axis? No, that's a little weird, isn't it? It's a little backwards. And so just for the horizontal shift, that number that's being added or subtracted, it's always going to be the opposite number than what's being added or subtracted. So if it says plus 4, it's actually going to move it to the left 4 if it's inside that absolute value. And the way that I always kind of try to remember that is if you think of this absolute value function like a parentheses, or it's like a grouping symbol, right? It's holding that plus 4 right next to the x. It's keeping it nice and tight together. Then that means it's going to move it in the x direction because it's kind of like contained with the x, as opposed to that previous one, that vertical translation, that plus 2 was outside of the x. It wasn't near it, so it moved it up and down. This one, it's stuck with the x, so it's going to move it in the x direction, which is left and right. But for some reason, whenever things are near the x, they get a little crazy, and they go the opposite direction than what you would expect. That's the only one that's a little backwards like that. So it is similar to the vertical translation because you're adding or subtracting, but it's just the opposite. If this said x minus 1, it would go to the right one, even though minus is normally to the left, but it's going to shift it over to the right. So those are your first two transformations, your horizontal and your vertical translation. Any questions yet on either of those? Okay. So the intention here is if you understand these transformations, like how the numbers added into the function change the graph itself, that you don't have to take time like getting out a graphing calculator or typing it in somewhere or doing a t-chart. You can just kind of look, oh, plus 4, it's just going to go left 4, and that's it. So now I'd like you to take a look at this graph. Go ahead and sketch this in your notebook real quick and make a note that the vertex is down here at -2, -3. So sketch that real quick. And what I want you to try to do is to write the equation of this graph. So thinking about how those horizontal and vertical translations move and how that would affect this graph. So you should write something like f of x equals, and then write the rest of that function. See if you can put those first two transformations together to kind of figure this out. So think about the horizontal shift and the vertical shift. And you're going to put both of those into that equation together. So it's adding or subtracting a number. So look back at those first two examples to figure out where the numbers go. Remember, we had one of them, you're adding or subtracting inside the absolute value. The other one, you're going to add or subtract outside of the absolute value. So look at that horizontal and that vertical shift. And so remember, you want to think about how this function moved from its original starting point, that parent function that originally had the v starting at 0, 0. So start from that point in mind, and then think, from 0, 0, how did it get down here to -2, -3? That one part of it, how did it move? And so I see, okay, well, first off, let's think left and right. If it started here, it went to the left 1, 2 units, right, from that origin. So I know that it had a shift, a horizontal shift to the left 2 units. After that, then it had a vertical shift down 1, 2, 3 units. So after that horizontal shift, it then had a vertical shift down 3 units. So these are going to be the two numbers I'm going to put into my equation. A horizontal shift. Now, I always think that horizontal shift, that's going to move it in the horizontal direction. That's the x-axis. So I know that this 2 is going to be grouped in with the x because it's in the x direction. So I'm going to draw the absolute value of x. But now we have to think, for the horizontal shift, it's going left 2. Now, that is the negative direction, but is this the normal one or is this the opposite? Would I write a +2 or a -2? What do you think? +2? Anyone agree? Yeah, that's right. Remember, for the x's, it's a little crazy. And so even though it's a left 2, we're going to write +2. It's just backwards for this one. So absolute value of x +2, then close that absolute value. Now we need to take into account that vertical shift. So that's this second number, this 3. So it's a shift vertically 3 units. So I'm going to add or subtract. Now, since it's in the y direction, do I flip the sign? Or if it's down 3, do I just write -3? Yeah, I'm getting nods for that second one. So down 3 units, I think, okay, -3. I'm just going to write -3 after it. So the final function, I'll just do it in one color to make it look nice for you. F of x equals the absolute value of x +2 minus 3. And so that right there is the equation for that graph on the left. And you just came up with that equation yourself just by looking at how it moved. Didn't need to do much analysis, didn't need fancy graphing software. You all did that yourself. Good job. Proud of you. This is easy, right? Should we take a test? No, we'll wait till next week for a test. What? Yeah, you'll be fine. All right, any questions on how I moved it or how I got those numbers yet? Okay. Or anyone at home, if you want to unmute to ask a question or just type it in, feel free to. I think they're okay. Moving on. Okay, the next thing we're going to look at is a vertical flip. Now, we've already seen that word vertical. We know that means up and down. And a flip, well, that's probably what you all did when you realized you were going to be in my algebra class, right? You flipped because you were so excited. right? Tiana? Yeah? No? So a flip just means it's, well, flipping upside down. Now notice my function, f of x equals, it says negative absolute value of x. So there's no numbers here for this vertical flip. There's just a negative sign. And that negative sign is going to flip our graph. So sketch that quick graph. And make sure you recognize that that vertex is still at the origin. It's still at 0, 0. So that didn't change. But the V is no longer facing upwards. The V flipped, and so now it's upside down. If you think about the pattern, with that original parent function, we started at the vertex and moved right one, up one, right one, up one. Since it flipped, all that's happening now is it's going right one, oops, right one, down one, right one, down one, right one, down one. So it's still that 1-to-1 ratio, that same like slope. I know you remember slope from Algebra 1. Who doesn't love rise over run? No. Okay, thought I'd try. So it's that same pattern, it's just down instead of up. Okay, and the only difference is this negative sign right in front. And just like my note there, that negative sign is outside of the absolute value function. Just like when we talked about the vertical and horizontal translations. Remember, one number was inside the absolute value grouped with the x, and that affected it in the x direction. The number that was outside of the x moved it in the y direction, or vertically. This negative sign is also outside of that absolute value, meaning it's like not grouped with the x. And since it's not grouped with the x, it's not in the x direction, it's in the y direction. It's vertical. So that's how I always keep those straight. If it's separated from the x somehow, then it's going to affect it in the y direction. If it is stuck inside with the x, then it's going to move it in the x direction. Hi, how's it going? You can sit there. Just like the vertical translation. Horizontal flip. So look at the one difference here. Where's that negative side located, everyone? Inside. Everything inside that absolute value affects it in the x direction. And I'm telling you, I do not care about this horizontal flip for this absolute value function. Why do I not care about this? Why does that not matter? Why is it nothing, Joy? Yeah, because the absolute value. Like if I make x negative and then take the absolute value of it, is it going to change at all? Doesn't that absolute value kind of cancel out that negative sign? It does. And furthermore, if you look at the graph itself, that V, if I took that V and I flip it horizontally, what's it going to look like? Same thing. It doesn't change, does it? If I flip this left and right, like if I reflect this over there and that over there, it's still going to be a V. It's going to be the exact same shape. It's perfectly symmetrical about that x-axis. If I flip it left and right, there's no change at all. So we don't really need to care about this, essentially. So if you ever see an absolute value with a negative in front of the x, just ignore it. It's not going to be anything you need to focus on or worry about for absolute value. Some of the functions we'll learn later this year, yeah, but for this one, it's no big deal. All right, any questions on that flip yet? Okay? Let's try putting some of these things together now. Here's your second example. Graph the following function. So I want you to write this equation out, sketch a quick coordinate plane from -3 to +3 on both axes. And I want you to take into account, well, there's two transformations now. I'm combining the translations with the flips. So I want you to try to sketch the graph of that v, of that new absolute value. What's it going to look like? I'll come around and take a look. So think about what each thing that I've added in there is going to do to our graph. How's it going to change it? All right, so we sketched some things out. Nice. I'm seeing some flips, which is good, and a shift, also good. So take a look at those earlier examples if you don't remember which way it moves. That's what those notes are for. So start by maybe writing out what the transformations are that are occurring. Is there a flip? Is there a shift? Which way does it move? And then try graphing it and see if it matches up. All right, go ahead and just show me with your hands. How many transformations do you see occurring on this graph? How many? 1, 2, 3, 4, 5, 500? Okay. 2, I also see 2 transformations. So first off, we have this negative that's out in front. So if it's in front of the absolute value sign, it's not grouped with it. That's separate from the x. So I'm thinking vertical. It's not in with the x. It's not horizontally. It's vertical. So that negative is going to be a flip. So I'm going to write this as a v flip. So I'm not going to graph anything yet. I just want to list all my transformations and then put it all together to draw that graph. So I know there's a vertical flip, meaning this v is going to be upside down. Next, inside the absolute value, there's a -2. Now that -2, it is grouped with the x, right? Because it's inside of the absolute value sign. That means it's going to affect it in the x direction, horizontally. Any numbers being added or subtracted are going to shift it in the x direction. The one thing we have to be careful of with these horizontal shifts, though, remember, when you're grouped with the x, it gets a little crazy. It does the right 2 units. So right 2 units. All right, those are the only transformations I see. Anyone else see something else? Did I miss anything? I think that's it, right? And we're going to graph it. So to graph it, remember our parent function, our starting point. From the origin at 0, 0. So that's where the V usually starts. So don't draw this. I'm just doing the baseline. Normally our graph starts right there. But this one has been shifted. So always plot the translations first. So I know it went right 2 units. So from the origin, I'm going to go right 1, 2 units and put the dot there. And that's going to be my real starting point at the point 0, I'm sorry, 2, 0. Then normally I draw my V, letter V, like opening upwards, but there was a vertical flip. So it's going to be opening downwards. Now, when I draw it downwards, don't just draw like, okay, there, V, whatever. You know, try to be a little more careful than that. We do want to be somewhat precise. And so remember that parent function. If you think of like the slope, we always went over 1, up 1, over 1, up 1. So what I'm going to do, starting from that vertex, is move over 1. But because it was flipped, instead of going up, I'm just going to move down. So from that point 2, 0, I'm going to go right 1, down 1, put a dot. Right 1, down 1, put a dot. And we're going to do the same thing to the left to make that upside down V. So I'm going to go left 1, down 1, left 1, down 1, left, down. There are my points. Now we just get to play connect the dots. Drawing that V, going to the lower right, going to the lower left. And that's it. That's your graph. Any questions on that? So now we're combining the translations with the flips. We're doing okay? All right, I'll take the head bobs. Would this graph be any different if I had a negative right there inside with the X? Would that change anything? Not really, right? Because that horizontal flip, it's going to look the same, upwards or downwards. All right, our last transformations are called stretch and compressions. So this first one we're looking at is a vertical stretch. So write the function out in here. Notice that there's a number in front of the absolute value. So what operation is going on between that 2 and that absolute value of X? Are they being multiplied together, added together, subtracted? What's that usually mean when they're right next to each other? What operation? Now that graph doesn't look too different. It's still a letter V, opens upwards, and I can see the vertex is at the origin at 0, 0. So did it change at all by multiplying by a 2 in front? Did that change the graph at all? What do you guys think? Did it do anything? All right, I'm getting a few head bobs. Anyone brave enough to tell me what they think is different? Allison? Good. Yeah, exactly right. That slope is different, you know. It's not to the right one, up one anymore. It's to the right one, up 2 units. Right one, up 2 units. So now it's going up 2 instead of just 1. Bless you. So what happened? Well, this 2 that's in front of it, it caused a vertical stretch. Meaning it's like if you grab the top and the bottom, it stretched it out upward. So it's like taller now. Almost if you had like silly putty or something and you stretch it out, it gets kind of skinny and narrow and gets taller and longer. So that 2 is just a multiplier. It's going to make it bigger, taller. It's stretched it out vertically. And if you look at any of these points, these coordinates, so normally we had a point on our original parent function at 1, 1. But the new point here is at 1, 2. So notice how the x coordinates are the same, right? I didn't do anything in the x direction. But if I look at the y coordinates, the vertical number, it's now a 2. Well, 2 is twice as big as 1, right? 1 times 2 is 2. So it's twice as tall now. Same thing's true with our second point. Normally we had a point at 2, 2 for our original parent function. Right here, this is 2, 2 on our parent function. But this new one, this transformed one, we've got a coordinate at 2, 4. Again, x coordinates don't change, but that y coordinate, it's now twice as big. Instead of a 2, it's a 4. 2 times 2 is 4. And that's going to be true for all those points. You're multiplying each of those y coordinates by 2. You're doubling them. So that's that vertical stretch. Questions on the vertical stretch? All right, sinking in, thinking about it. Okay, we have one last transformation. Let's take a look. A vertical compression. Now the word compression means to squish together. Vertical compressions. Go ahead and write that function. It's f of x equals 1/3 times the absolute value of x. And then go ahead and sketch that graph. And be careful about where each of these points are. So we still have the origin for the vertex, but then our first points, well, this is going to be 3, 1. And over here, this is -3, 1. So make sure you hit those points on your sketch. All right, so we've got the graph down. And this is a vertical compression. So you think about a compression, if I took this graph, this V shape on the top and bottom, and I squished it down. All right, so if you ever had like silly putting, you squish something, what happens to it? Where's it go? Where's everything move? Kind of like gets squished out to the sides, right? When you squish something down, it gets like, I can't demonstrate it with myself. I can't squish my own body, but you get the idea. So that's kind of what's happening here. We are squishing the graph vertically. I'm compressing it downwards. But there's a number in front of the x, absolute values of x sign, just like for the vertical stretch. So what's the difference between the two? Can you think of why this is a compression versus a stretch? The previous one I had 2 times the absolute value of x. This is 1/3 times the absolute value of x. Still, there's a number in the same place being multiplied. But why is this a compression instead of a stretch? Any ideas, Mason? Taylor? No difference? Raina? No? Aaron? Because of the number in front, okay, where it was a 2, that's just a number up top, where this is like a fraction with the slope. Are you thinking about that, like rise over run? Yeah, that works. If you remember rise over run from algebra 1, that'd be the rise, that's the run. So 1/3. From the origin, I'm going up 1, right 1, 2, 3. That works, right? That is slope. Just like on the previous page, this is 2. Technically, it's like a 2/1, but we never write that 1. From here, I'm going up 2 and right 1. So it's just a difference of the slope. Now, if your graph is getting stretched up and down, then you're going to have a bigger number up top, a larger run or rise. But for this one, the number in the denominator is bigger. Well, that's your run. That's your horizontal, meaning you're going to move more units to the left and right than you are up and down. So the key difference here is going to be looking at this number and seeing basically, is it bigger than 1 or less than 1? Because right at 1, that's when the numerator and the denominator are the same. If the numerator is bigger, then it's going to be taller. You've got more of a rise. If the denominator is bigger, it's going to be wider because you've got more of a run with that slope relationship. Okay? So this essentially is saying, take that absolute value graph, that V, and now on the that vertical stretch, we had the number 2, and it was 2 times as tall. Here, it's going to be 1/3 as tall. Now, if you take 1/3 of something, it's going to be shorter. Like if you're 6 feet tall, I'm going to say, now, what's 1/3 of your height? Well, that's only 2, a much smaller number than that 6 originally. So if I think of any of these points, the original points on that parent function, 1, 1, 2, 2, 3, 3, I'm taking the height of each one of those points and I'm taking 1/3 of it. It's like I'm dividing them by 3. That's kind of what this fraction in front does, right? It's saying 1 and divide that number by 3. Take 1/3 of it. And if I look at this first point at 1, 1, the new point down there, does it look like that's approximately 1/3 of the distance between 0 and 1? It's hard to see exactly, but that's pretty close, 1/3 of it. It's really easy to see with a point like there. That's a multiple of 3. So this coordinate is 3, 3. And if we look at the y value, that second number, that's our parent function. On this new graph, we want 1/3 of that. Well, what's 1/3 of 3? Don't all shout at once. It's hard to understand it when you do that. Caleb? Yeah, it's 1. And if I look down here, look at this coordinate, 3, 1, and notice that y value is 1. It's 1/3 of 3. I took that number and I divided it by 3, and I got 1. And so that's what this graph is showing. It's 1/3 of the height of that original 1. So if this number in front is ever a fraction or a decimal even, something that's less than 1, then it's going to be a vertical compression. It's going to be shorter. But if it's a number bigger than 1, then it's going to be a vertical stretch. It's going to get taller. You're multiplying that y coordinate by much bigger numbers. It's going to shoot up pretty quickly because there's more of a rise. Any other questions on these? The vertical stretch and compression. Okay, we're doing all right. Now, I didn't talk about this at all, but do you have an idea of what would happen if we had a function? You don't need to write this down, but you can just think about it. What if I had that number inside the absolute value? Based on what you've learned about all these other transformations today. A what? Like a vertical stretch still? So with this 2, instead of being out in front, that was our vertical stretch. But if it's inside the absolute value, grouped with the x, what do you think it would do? Nothing? No change? Well, think about the other types of transformations we learned, like the shifting and the flipping. Remember how if something was outside of the absolute value, it did one thing in one direction. But if it were inside the absolute value sign, it changed it in a different direction. So when the 2, this number in front that's being multiplied, when it was out in front of the absolute value, it was a vertical stretch. This is inside, it's grouped with the x. So is that going to stretch it vertically, do you think? Horizontal. Yeah. If it's grouped with the x, it's going to affect it in the x direction, the horizontal direction. So if I put a number there, that'd be a horizontal stretch. If it were a fraction, a number less than 1, it'd be a horizontal compression because it's going to affect it in the x direction. But I'm not going to teach this at all. I'm not going to show you this because if we think about this like vertical compression, that's like I'm squishing it from the top and bottom, right? Squishing it together. But what if I took this graph and I did a horizontal stretch? If I pulled this out to the side, wouldn't it look kind of the same? Like if this graph, couldn't I have either squished the top and the bottom together or pulled it out to the sides? Would I get the same shape? Looking for nods or no's or some type of affirmation. Do you see what I'm referring to? So like a vertical compression would look the same way as a horizontal stretch. Or a vertical stretch would look the same as a horizontal compression. Is if I like squished the left and the right sides together, it would look the same way as if I took the top and the bottom and I pulled them apart. So because there's no real way when looking at a graph to determine if that were a horizontal stretch or a vertical compression or whatever, I basically am just not ever going to assess you on any horizontal stretches or horizontal compressions, okay? You just have to know it for the vertical. You'll only have these numbers out in front of the absolute value. Sound good? It's less stuff for you to worry about or think about. So those are all of our transformations that we're going to look at for this absolute value. And each one of them has a different part of this new function. So let's jot this down, and we're going to kind of make a little cheat sheet for what happens to our graph whenever there's a number in each of these different spots. All right, so go ahead and write this function down. F of x equals a, absolute value of x minus h, close the absolute value, plus k. So I'm putting in these letters of A, H, and K, and those are just the different spots in this equation where you could have a number. And based on where that number is located, it's going to change our graph, our V shape, in some way, shape, or form. So let's make a little breakdown so we have all this info in one place with one spot. The first thing we have is A. And what does A do to our graph? What does that cause? How does it change the V shape? What words did we use? Go ahead and check back on your notes. What was that called? Yes, a vertical stretch, or it could be a vertical compression. Right, right. So let's make a note of each of these. So A, that's going to either cause a vertical stretch. I'm just going to write a V stretch. Or a vertical compression. So it's going to cause one of those two things. A vertical stretch, it's going to get like taller, or vertical compression, it's going to get squished together from the top and bottom. Now, in order to differentiate between these two, what do we look for? How do I know, based on that number, that's A, that number in front, how do I know if it's going to be a stretch or a compression? What do I look for, or what do I compare it with? That's it. You compare it to the number 1. Is it bigger than 1 or is it less than 1? Exactly. So the vertical stretch occurs when A is greater than 1. Remember those inequality signs? So if A is greater than 1, it's going to be a vertical stretch, meaning it's going to be kind of narrow and skinny and like really tall. But if A is less than 1, then we're going to get a vertical compression. It's as if we squished it from the top down. It's going to kind of be wider out to the sides. Hey, what do you think would happen if A were equal to 1? Would that change the graph? No. Why wouldn't it? What happens if you multiply something by 1? It's the same thing, you know? If you multiply x by 1, it's still x. There's no change at all. That's why we only care if it's bigger than 1 or less than 1. Nice. Now, there's one other thing that could happen to A, or something that could be in front of A, right here. What else do we need to look for in front of that function? Yeah, a negative sign. If there is a negative sign, Lauren, what's going to happen to the graph? Exactly. So one thing we need to look for is this can also be a vertical flip or a V flip. And that's just if there's a negative sign. Okay, so if there's a negative sign in front, that's going to cause a vertical flip. Our V is going to be upside down. An important thing to note with this negative sign, though, is make sure that you don't use that negative sign when you're determining if it's a stretch or a compression. Because if I had a function that was like -5 times the absolute value of x, I see that A is like a -5. And if I'm determining if it's a stretch or compression, I might get confused and say, hey, wait, -5, that's definitely less than 1, right? Because all negative numbers are going to be less than 1. But that's not the case. This would be a stretch. That negative sign just flips it. So whenever you're comparing it to A, ignore the negative sign. Just look at that actual number in front. All the negative sign is going to do is tell you if it's a vertical flip or not. Once you know if it's an upwards V or a downwards V, ignore the negative sign and then compare the number that's left over to 1. Now, is that number bigger than 1 or less than 1? And that's going to be how you know if it's that stretch or that compression. All right, next up, H. So this is a number that's being subtracted from X. It's inside the absolute value. And what does it do? Look back at your note to those earlier examples. If you're adding or subtracting a number inside the absolute value, horizontal translation. That's right. That's a horizontal translation. It's going to move it left and right. So that's a, oops, horizontal or an H shift, if you want to just abbreviate that. That's a horizontal shift. It's going to move it left and right in the horizontal direction or in the X direction. But what's the one thing you had to be careful with for just this horizontal shift that you might mix up? That opposite sign. So put a little note here, just in parentheses, just write, hey, it's the opposite of the sign. So it's the opposite direction of whatever the sign is. So if it says +3, you're actually going to move it to the left 3. Oops. Just make sure that you use the opposite direction of the sign. -5 means you go right 5. It's the horizontal shift. The last piece we have is K. What does K do? If I've got a number that I'm adding or subtracting that's completely outside of the absolute value, what's it do to our graph? That's it. That's the vertical shift. It's going in the Y direction because it's not grouped with the X. So I'm going to write V shift. So that K just does a vertical shift to our graph. Is it the opposite sign as well? Do I have to flip it like we did with the horizontal? No, this one's normal. No changes there. All right, so that's it. That's your summary of all the transformations that can occur to an absolute value function. Now, what you're going to have to do is put all of these together. So I've got 2 examples for you that we're going to work on now. All right, see what you have learned from this. Please use your notes, look at the examples to try to figure these out. So, example 3. I've got a graph on here of this absolute value function. And your job is to write that entire equation. So write that whole f of x equals, then you're going to write the rest of it. So go ahead and sketch the quick graph. Here's the important points. I'll plot those for you. So you've got a vertex up here at 0, 5. Then you've got points at 1, 2, and 2, -1. So make sure when you sketch this out, you hit those points. Then over here at -1, 2, and down there at -2, -1. So make sure your sketch hits those 5 points and write the equation of that. Start off by listing all the transformations you see. So think about the parent function starting at the origin at 0, 0. How did it move? How did it change? How did it stretch, compress, shift up, down, left, right? Did it flip? All that good stuff. So start off by just listing every transformation that you observe. And once you have those listed, then you can put all those numbers or signs and symbols into your equation. Hey, how's it going? Nice job. All right, so if it helps, write out each of those transformations. So some things that I noticed right off the bat is this is not a V, it's upside down. So I know that there's a vertical flip. So I'm going to list that. I've got a total of 3 transformations here, and I'm going to include each one of them. The first thing I notice is a vertical flip. All right, now what else happened? Did that vertex move? Yeah, which way did it move? Up, down, left, or right? And by how much? After that, think about any stretches. Did it follow our parent function's 1, 1 pattern, that same slope? Or is it like taller? Was it stretched out vertically? And if it was, by how much? Like how many more times taller or how many times shorter is it compared to our parent function? So think about those. We're going to take one more walk around. If you've got it written down, let me take a look. Yeah. Let me write you a pass. Yeah, no problem. Nice. Okay. Listen the transformations. Awesome. Cool. Yep. Oh, you're still thinking. Nice. Good job. All right, so that vertex is clearly not at the origin. It's up at 0, 5. So there's been a shift from 0, 0, all the way up to 0, 5. That's a vertical shift up 5 units. So I'm going to list that next. Up 5. So it's upside down V, vertical flip. Vertex went up 5 units. And then finally, the stretch, right? Because from this vertex, over 1, down 1, well, that's what our parent function would be, but it's not going down 1. It's going right 1, down 1, 2, 3. That's 3 times the usual height, 3 times the normal motion. So I know that it's been stretched. It's taller, right? It's like narrower. And so I'm going to say there's been a V stretch, a vertical stretch. And you have to list the number, like by how much. So how much was it stretched by? Autumn, what's that stretch? By how many times? So how much taller is this? Yeah, exactly. It's 3 times taller than your parent function. So it's a vertical stretch by 3. So those are going to be our 3 transformations. We've got to then write this function, this absolute value function, with all those transformations listed inside of it. Here we go. F of x equals. First off, there's a vertical flip. For vertical flip, that means we're starting off with a negative sign. That negative indicates this flip. That's part of A, right? Only if there's a vertical flip, we put a negative in. Next, the vertical stretch or compression. Whatever that number is, that factor that it was stretched or compressed by, that number is A. So in this case, it's a 3. So I'm just going to write this as -3. Then we're going to have our absolute value of x. And now we have to think about this translation, because I know that that translation, that shift, means I'm going to add or subtract something. But I have to think about, am I going to add or subtract this number inside the absolute value or outside? Should I put it here, inside the absolute value? Yes, no. No, so remember, anything inside with the x is going to move it in the x direction. But because this was a vertical shift, that's in the y direction. So I don't want it kind of stuck together with the x. I want it separate from that x. So I'm going to close off the absolute value, all right, because it's not moving in the x direction. It's moving in the y direction. And it just went up 5 units. So I'm just going to write plus 5. Because that's that vertical shift. I don't need to change the sign. It's a plus because it's up 5. And this right here is our function. We've got it. That is the equation for that graph right there. And you all did it. That's great. You came up with it from your own brains. That's awesome. Any questions on any piece of this function or any of these transformations that you're unsure about or you're a little confused on, that you didn't remember how I got a certain number or why I wrote something in the equation? Got one more for you. Are you ready? It's going to be epic. Here we go. So this last example, we're doing the opposite. This is the main part of this learning target. Remember, the main skill I want you to be able to do today is to graph an absolute value function. So this is the main quintessential skill from today. I've got an equation here. It's absolute value because it's got those absolute value bars. Right? There and there. But there's a bunch of other stuff in there. So your job right now is to try to graph this. I want you to sketch a graph of this exact absolute value function. Now, just like I've been doing in my examples, what I want you to do first, after you write the equation and sketch a coordinate plane, is I want you to list the transformations. And I'll give you a hint. There are 3 of them. So just list the transformations like I've been doing on my previous examples. What are each of those different numbers doing to our graph? So don't even worry about drawing it yet. Just list them out. What's one thing that's happening? What's the second thing happening? And the third. Are there translations? Are there flips? Are there stretches? Are there compressions? And if so, by how much? Just write them all out. Look at each number in each place. This is a great time to look at the general format equation that I did earlier when I kind of broke down what A, H, and K each do. That's exactly the time to use that little note. So what is A going to do? H and K. What does each piece do? And then sketch that graph. Yep, look back at those examples. Try to think about what each number is going to do to the graph. How's it going to change it? How's it going to move it? Again, just make a list. 1, 2, 3 in this case, 3 transformations that I see occurring. And what are they? What are each of those going to do to our graph? And look carefully at the different signs, how it's going to change it, and in which direction. Cool. Looks good. Awesome. Yeah. All right, so if I'm looking at this, I'm just going to go right in order from left to right and look at each new addition in there and think about what each of those do. So first off, there's a 1/2. This is in front of my absolute value function. It's being multiplied. That means it's going to be a vertical stretch or a vertical compression. And to determine which one of those it is, I have to figure out, well, is this number bigger than 1 or less than 1? All right, so 1/2. Is it bigger than 1 or less than 1? Less than. Good job. So is that going to be a vertical stretch or a vertical compression? compression. It's going to be squished down, right? So I'm going to write this is a vertical compression whoa, by 1/2, right? Whatever that number is, that A, that tells us how much it's going to be stretched or compressed by. So this means that from our basic parent function, there's going to be 1/2 of the original height. So instead of over 1 up 1, it's going to be over 1 up half, over 1 up half that distance. Next up, I see x plus 3. Now that's inside of the absolute value. Adding or subtracting a number causes a translation. Is this going to be horizontal or vertical? You just show me with your hands if you want. Go left and right or up and down. What do you think? All right, it's grouped with the x. It's inside of those absolute value bars. So it's going to be a horizontal translation. So it's going to move left or right. That says plus 3, but for the x direction, you always flip the sign. Even though it's a plus 3, we actually are going to move it to the left 3 units. It just changes, just for that x direction. And finally, the last piece we have is plus 2. Now that is outside of the absolute value sign. It's separate from the x, meaning it's not going to move in the x direction. It's going to go in the y direction. So that's vertical. We don't change the sign for a vertical translation. So I'm just going to draw an up arrow 2 units. So this is a vertical shift up 2 units. So those are all the transformations I see. There's nothing else kind of added into that equation. So now we just have to graph it. To start graphing this, I always think about that basic parent function and that vertex. That's like our starting point. Normally, it would start at 0, 0 at the origin, but that's not the case for this one. It's been shifted. It's been moved around. So I look at my different shifts. It's gone left 3 and up 2 units. So from the origin, I'm going to go left 1, 2, 3, and then I'm going to move up, left 3 units, then up 1, 2 units. And that's going to be my starting point. So I'm going to draw my vertex starting at the point -3, 2, because it went left 3 units and then up 2 units. Now it wasn't flipped, so it is going to be a V opening upwards like the letter V, but I have to take this compression into account by 1/2. Now normally with our parent function, from the vertex, I simply go right 1, up 1, right 1, up 1, like your standard slope of 1. But this, it's been compressed by 1/2. So from this starting point, I'm going to go right 1, but I'm only going to go up 1/2. It's half of the original distance. So right 1, up 1/2. I'm going to continue that pattern. From this point, I'm going to go right 1, up 1/2. It's only going up half the distance every time. Right 1, up half, right 1, up half. So it should make it all the way to the point 1, 4. Now that same property is going to hold true for going to the left. From the vertex, I'm going to move left 1, but move up just half the distance, left 1, up half the distance. Then go ahead, connect those dots. And that's your graph. You did it. Hooray. Who has questions? Anything at all that you want to ask about or me to go over again that you're unsure of? Yeah, because you're like, plus, that's positive. It should go to the right. The reason why this is the opposite, that's always going to be true for that x, for that horizontal direction. And that's based off of just this generic equation, the format where it's x minus h, because it's that minus sign, it's going to be always the opposite direction. Because it's like if I'm subtracting a -3, that would look like a +3. So you take the opposite sign just for the horizontal direction, just because the x is weird. Other questions? Or anyone at home, if you have a question also. All right. Then grab out your Chromebooks. We're going to take a look at our homework for tonight. Oops. So we are all going to go to the website, deltamath.com. And your screen is going to look very different because I have a teacher account. So I have all these things. You should just have one assignment in there called absolute value or graphing absolute value functions. So let me show you one of these problems. And we can do it together. And I'll kind of show you how Delta Math is going to work for these problems. So up on the board, you see I've got this function y equals absolute value of x minus 5. Remember, y, that's just the same thing as f of x. They're just different ways of writing it. I look at my absolute value here, and I see absolute value of x minus 5. So there's a minus 5. If you check out your notes, you should keep those handy for reference. You should recall, oh, that's a horizontal shift, this horizontal translation. But it's always going to be the opposite direction. And so if it says minus 5, it actually means I'm going to move it to the right 5 units. So I'm going to take this V shape right here, which look, it's just like our parent function, origin at 0, 0. You see that slope 1, 1, over 1, up 1, over 1, up 1. And in order to graph this, you're just going to move these dots. Now, if I move any of the blue ones, it's going to change the opening of it. So this would be if I had like a vertical stretch or compression, I'd move the blue ones. Or if there's a vertical flip, I could just move this down to the bottom to make it upside down. But in this case, all we have is this minus 5. So that's a vertical shift. So to do those shifts, just like when I was graphing them by hand, we're just going to move the vertex. So grab the green dot right here, and a negative 5 means you want to go right 5. So go right 1, 2, 3, 4, 5. Leave it right there. And so this would be the graph of this. You're transforming that basic parent function. Hit submit answer, and you got it. You'll notice on Delta Math, it always shows you what actually you did. It kind of breaks it down. This is going to be a shift right 5 units, which helps you out. And then you'll go to the next problem. On Delta Math, there are always these help videos that you can watch again. If you're confused, if you're like, wait, I thought I had this right, you can watch those. On your screen in the upper right-hand corner, there should be a little demo that says like show example that you can watch or look at to give you some help. Or again, as I mentioned at the beginning of the lesson, I've got these videos posted online, so you can rewatch my lesson at any point to help you out. So we've got about 5 minutes left. Go through some of these questions, okay? I want you to work until the bell rings. Try getting through these, work through them. This is your first assignment. It's 10 problems, and it will just be due by our next class period. So on Friday for you. Yeah, Caleb? It's not working? All right. Let me stop the recording, and I will be right over.